So today, as I mentioned, we're going to look at 10.4 hyperbolas. Remember our different conic sections. Straight across on a cone would be circle. At a diagonal through the cone would be an ellipse. At a diagonal through part of the cone would be a parabola. And straight down through both cones is a hyperbola. So a hyperbola is going to end up having two sections to it. So we are going to talk about how to write the equations of hyperbolas and graphs, find the asymptotes, sketch hyperbolas, and then we're going to look at the properties of hyperbolas to solve a real life problem. And then we're going to talk about how to classify conics from the general equation. So a lot of this stuff, again, is review from Algebra 2, but it's important to know. So the definition of a hyperbola is the set of points called a locus. Again, remember that the term locus refers to a set of points that fit some criteria. Well, what's the criteria? The absolute difference whose distance from two foci is constant. So I've got a one focus here, one focus here. The difference, if I take any point, that difference will be a constant. Now, you don't really have to worry about that too much. What we're going to worry more about are the equations here. We have a vertical and a horizontal type. And like I said, the hyperbola has two branches to it. So a horizontal, my major axis, also called the transverse axis, runs through the middle of both sides horizontally. A vertical hyperbola, the transverse axis cuts through both sides of the hyperbola vertically. So the center, the two vertices, and the two foci are all on the same line. So this would be vertical. Here, they're all horizontal. The way to tell that from the basic equation is which one is negative. So in this case, x term is positive and y is negative. That makes a horizontal. In this case, my y and x are switched. The y is positive, y term is positive, the x term is negative. That's vertical. So the A is always under the positive. The B is always under the negative on the negative side. Now, when we're talking about the eccentricity of it, it's going to turn out to be greater than 1. So for ellipses, we were talking about the eccentricity being less than 1, but here it's going to be greater than 1. And the reason is that the focus is outside of or is a greater distance from the vertex than from the center than the vertex is. So C is greater than A. So C is going to be a value larger than A. So my eccentricity is greater than 1 then. All right. If I have, this would be the standard equation. If my center is at the origin, and again, my H and K would be the center if it's transposed left, right, up, or down. The transverse axis, like I said before, I called it the major axis, is the one that goes through both sides of the hyperbola. The minor axis is the one that cuts between the two branches of the hyperbola. This one is also called a conjugate axis. I typically use major and minor, but you might see those terms. And if you want to, there is a video about more about hyperbolas. It's pretty interesting, but I didn't want to take class time right now. So here I've got an equation. I can tell it's a hyperbola because my x term and my y term are not the same sign. So it's a y squared term minus an x squared term, which tells me it's going to be vertical. So I know a few things. First of all, my center is at -3, 1, because my h is -3 from here, and my k is 1. My value of a is the square root of 1/4, which is 1/2. My vertex then, since it's vertical, is going to be at -3, and then 1 plus a and 1 minus a are going to be my two vertices. So that turns out to be -3 and 3/2, -3 and 1/2. B is the square root of b squared under the x squared term there. So that's going to be 1/4. And my c squared, and to calculate c, the distance to the focus, is going to be 1/4 or 1/2 squared, which is 1/4, plus 1/4 squared, which is 1/16, is 5/16. So the value of c is the square root of 5/4. We could use our calculators to come up with a decimal approximation if we wanted to graph that. My focus then is going to be along the same axis as the vertex. So it's going to be -3, 1 plus square root of 5/4, and -3, 1 minus square root of 5/4. So those would be okay. My asymptotes. Okay, we didn't talk too much about this, but I should probably go to the previous slide. Just real quickly, I'll come back to this. The asymptotes for a horizontal turn out to be y is equal to plus or minus b over a times x. And that is going to be these two dotted red lines. They're not part of the hyperbola, but they're guidelines to help us graph it, because these lines will get closer and closer to the asymptotes, but never touch them. So that's a guide for graphing. Another guide for graphing is this rectangle in the middle here. The A is the midpoint of one side, the vertices, and the B term, my co-vertex, is the midpoint of the other side. So if I draw this rectangle in the middle, the asymptotes will go through the rectangle, through the corners, through the vertices of the rectangle. So that's another guide for graphing, to make it easier than plugging in points and trying to figure out what the values are. Use the guidelines and it will make your graphing much, much easier. So let's go back to the problem we were on. The asymptotes are going to be, since my A term is 1/2 and my B term is 1/4, my asymptote is going to be y equals plus or minus A over B, because it is a vertical. times x. And 1/2 divided by 1/4 is equal to 2. So my two asymptotes are going to be my y term, which is y minus 1, plus or minus 2 times my x term, which is x plus 3. You have to include the h and k, right? So my eccentricity is c divided by a, which turns out to be a square root of 5/2. And if I were to graph this thing, it's a little hard to see, but my center is at -3, 1. My a term is 1/2. So -3, 1 plus 1/2 gives me 3/2, minus 1/2 gives me 1/2. So those are my a's. My b term is going to be 1/4. So it's going to be -3 minus 1/4 is -13/4, 1. -3 plus 1/4 is -11/4 and 1. So there's my A and A, B and B, my vertices and my co-vertices. I can draw a rectangle with those as the midpoints. And my asymptotes are going to go through those corners. And the equation of those are going to be this. But if I can draw the box, I can draw the asymptotes. Question?
Isn't the asymptote supposed to be like plus minus b over a x?
For
Asymptote. That was the formula. Is that what you want us to write?
E or ax for a I'm sorry, for a vertical, it's plus minus a over bx. I had the wrong side. Sorry. So we have a vertical here, so it is plus or minus b over ax. So you'll notice I never did actually plot any points on the hyperbola except the vertices. And I just use the rest as a guideline. So yes. So it's my y term, which including the k, so y minus 1. So it's y minus k equals plus or minus a over b times x minus h. And 1/2 divided by 1/4 is equal to 2. So you're going to have two asymptotes. They're going to be reflections of each other, right? Going through the center and going through the corners of that rectangle. Again, the asymptotes and the rectangle are not part of the hyperbola, but they are guides to help us graph it. Okay, so that one we had the equation and had to graph it, but you might encounter one where you're just given some information. Well, this one's still, the next one's still an equation, but we do have to put it into standard form for a hyperbola. Again, it's a y squared term minus an x squared term, so it's going to be vertical, but I'm going to divide through by 18. So I can put it in the form of a standard form of a hyperbola. So that tells me my center, I have no h and k, so that's going to be 0, 0. So that's nice. my A turns out to be the square root of 3, and my B turns out to be the square root of 6. My vertex, we said, was that is going to be 0 plus or minus A, because this is 0 again. I could have put a 0 in there. My B turns out to be the square root of 6. And C squared equals A squared plus B squared is going to be the square root of 9, which is equal to 3. So my focus, again, is along that major axis. So it's going to be along the same axis with the vertices. So I'm going to add 3 and subtract 3 along to the y coordinate. Again, we could have imagined there's a 0 there from my center, right? So my asymptote y minus k squared equals, again, plus or minus a over b x minus h squared. An a, not a 9. H and k are just 0. A is square root of 3. B is square root of 6. That reduces to 1 over the square root of 2. And again, you don't have to necessarily rationalize this. We can just leave it like that for now. My eccentricity is C divided by A, which is square root of 3. So if I graph this, again, it's going to be vertical. You'll notice that my B is larger than A, which means this thing's going to be flatter than the last example we did. And it's going to look like this, where my center is the origin, and along the major axis, 0, comma 0 plus the square root of 3 and minus the square root of 3 are my A's. My B, 0, 0, and I'm going to my x term, 0 plus root 6 and negative root 6, 0. So those are the centers of my or midpoints of my rectangle. My asymptotes then go through the corners of the rectangle. And again, the only points on the hyperbola that I actually graph are the vertices there. Yes.
Just to clarify, for the equation for the asymptote, it's not supposed to be square, right? It's just supposed to be y minus k equals 4. Yeah.
Oh, not squared. Not
I'll be
squared.
going crazy.
They are linear. Yes, I'm sorry. Thank you. Very good. 5 pretend bonus points for you.
Yeah,
I just wanted to make sure I wasn't like.
No, you were right. You are correct. Yes, they are obviously lines. It'd be kind of weird if your asymptote was not a line. Yeah. All right, very good. Now, you may not have an equation. You might just have information that you have to come up with the equation. For instance, if I have something like this where I know the focus and I know the asymptotes, I can still come up with the graph. It takes a little bit of work, but I can do it. So my focus is at plus and minus 10, 0. So it's going to be horizontal. My C is going to be equal to 10, square root of, and the C squared is 100. And now I know that my ratio, since this is horizontal, of B to A is 3 to 4, but that doesn't mean that B is equal to 3 and A is equal to 4, just means the ratio. And if I do a little bit of trial and error, I'm going to figure out that B is equal to 6 and A is equal to 8 because A squared plus B squared has to be equal to C squared. So 64 plus 36 is equal to 100. So that tells me that, again, it's horizontal, so my x squared is the positive term. X squared over A squared minus y squared over B squared is equal to 1. So my eccentricity is C divided by A, which is going to be 10 divided by 8, or 5/4. And if I wanted to graph this, my A term is 8. So from the origin, 0 plus 8 is 8, comma 0, and negative 8, comma 0. My B term, my minor axis, 0 and 0 plus 6, 0 and 0 minus 6. So there's my rectangle. Here are my asymptotes. Yes.
How does eccentricity relate to like the equivalent?
Well, and so the greater the eccentricity, the more flattened out, if it's horizontal, the more flat and skinny it is. As the eccentricity is closer to 1, that means that my focus isn't too far from my vertex, so it's going to be a lot more up and down. So.
For like, is it still measuring technically how oval something is?
Well, yeah. So if
Yeah.
let's say E was, let's say, equal to something like 10, that means it's going to be a lot more like this. If it's closer to 1, let's just say it's equal to 2 or something, it's going to be a lot more up and long way. Well, if it was vertical like that, but it'd be a lot more.
And then related to rational functions.
To rational functions?
Like the thingies where it's like graph similarly. I forgot what they're called. They're rational.
Like this?
Well, no, a bunch of equations, variables, like x squared over x minus blah blah blah. And you have to I don't know. I just remember I really disliked them in algebra 2.
Oh, I know what you're talking about, like functions over functions.
Yeah.
Not necessarily, no.
Then if it's technically, if it's less than 1, then the lines are gonna face inward, creating the oval.
Yeah. So the eccentricity was less than 1. It's going to be turn out to be ellipse. Yes. Or what?
A solid or dash.
What? As long as I can tell what it is, yeah, it doesn't matter. Usually I just do dashed lines, just because to remind myself it's not part of the graph. It's just a guideline, but it doesn't really matter, no. So we might have an equation like this, where I know the vertices, and this is a typo. The center is not at the origin, so you can just scratch that out. I can't reach that high. The center, if it passes through, if it's at 1 plus or minus 2, that tells me the center is at 1, 0. And the center is not at the origin. So you can just X that out on top. So if the center is at 1, 0 and A is equal to 2, I don't know what B or C are. So I have to solve And I can solve for B because I can write this equation. My vertices are at 1 plus or minus 2, so it's going to be vertical because it's up and down. That means that my A squared is 4, and I don't know what B squared is. So if I write my equation like this, y minus k, x minus h, both squared, over a squared, over b squared, which I don't know, I can plug in the value I do know for x and y and come up with a value for b. So let's do that. I'm going to plug in square root of 5 for y, and I'm going to plug in 0 for x. So I've got here now 5/4 minus 1 over b squared is equal to 1, or 1 over b squared is equal to 1/4, which tells me b is equal to 2. So now I have a and b. I can calculate c now. Well, I can first write my equation, right? Because I have a and b. A and b happen to be the same exact value, which tells me I'm going to have a square for my rectangle in the middle, but that's okay. So I've got y squared divided by 4 minus x minus 1 squared divided by 4 equals 1. My c is equal to a squared plus b squared is 8, is c squared. So c is equal to the square root of 8. My asymptotes are going to be y equals plus or minus, well, b and a are the same thing. So 1 times my x value of x minus 1. So those are my asymptotes, x minus 1, x plus 1. My eccentricity turns out to be square root of 2. And my graph is going to look something like this. Again, I could have drawn a box, something like this. So this would be at, just for reference, 0, 3. And this, I'm sorry, 3, 0. This would be at -1, 0. This point would be at 1, 2, and this point would be at 1, -2. And point 0 square root of 5 is right there. And that's the one that we said we went through. Right? All right, well, where are hyperbolas used in reality? Well, some celestial bodies like comets actually have hyperbolic orbits, which means this is my sun here. And my comet comes in like this, and the sun is at the focus, and it goes out like this. It passes by the sun one time. That's it. Comes in, goes out. That's it on a hyperbolic orbit. But there are comets that do have hyperbolic orbits. They only pass by the sun one time. Hyperbolas are also used in mirrors for telescopes and things like that. So that's the problem that we're going to look at next. So let's take a look at a hyperbolic mirror used in some telescopes. It has a property that a light directed at a focus will be reflected to the other focus. The focus of the hyperbolic mirror has the coordinates 24, 0. Find the vertex of the mirror if the mount at the top edge of the mirror has coordinates 24, 24. So that is on the hyperbola. So I know my C, but I don't know A or B. So this one gets a little bit trickier. I can write it as my origin is the center. So x squared over a squared minus y squared over b squared equals 1. I don't know what a and b are, but I do know that a squared plus b squared is going to equal 24 squared, because that's where my focus is. So I can write this in terms of a squared, and I can represent b squared as 24 squared minus a squared, and plug those two values into this equation and solve for a squared. Gets to be a little bit tricky, but we can do it. So I've got x squared divided by a squared minus y squared divided by 24 squared minus a squared equals 1. Now I know that 24 is on the hyperbola. So I can plug that in for my x and my y values. So I've got 576 divided by a squared minus 576 divided by 576 minus a squared equals 1. So now I have one equation, one variable, I can solve it. It's going to take a little bit of work, but I can solve it. I need to find get rid of this denominator, so I'm going to multiply through by a squared and 576 minus a squared to get rid of the denominator. What is that going to look like then? That's going to look like 576, my first term here, times 576 minus a squared. If I multiply by a squared, those will cancel out, so I'm left with these two terms, minus 576 times a squared, and the 576 minus a squared, that term canceled out for this term, and then 1 times a squared and times 576 minus a squared. So it's no different than we've been doing since algebra 1 to get rid of a denominator, but it's just a little bit trickier now. So what do I have? I have 576 times 576, so that's 576 squared. I have minus 576a squared. I have minus 576a squared. Here I've got 576a squared that I have to subtract from this side as well. So I've got minus 3 times 576a squared. And I have a squared times a squared is negative a to the fourth. Bring it to this side, it's positive a to the fourth. So now I have a quadratic, but it's to the fourth power. So if I solve this using a quadratic equation, and you could use your calculators to do this, I come up with two values for a squared. And my values are 1507 or 220 using a quadratic equation on that. That's what a squared is equal to. So I've got a quadratic within a quadratic here. If I look at this one, a squared is equal to approximately 1500, whatever, 8. Take the square root of that, it's going to be approximately 39. Well, if I had 39 as a squared, b squared equals 24 squared minus 39 squared, that's going to turn out to be negative. So what does that mean? That means this is an extraneous solution. Because my b squared can't be negative. So that leaves me with 220 as a squared. I can take the square root of that. It turns out to be close to 15. And that is what a is equal to. Well, that's going to be my vertex, right? Because my vertex is going to be 24. I'm sorry, my vertex is 0. The center is 0, 0. So my vertex is 0 plus a 14.8, whatever, 0. And that's all it asked for. We don't have to find the asymptotes or any other values, right? Yes,
How did you solve these?
quadratic equation. Okay, so don't forget your quadratic equation. You have to do 3 times. But remember that I'm solving for a squared, right? So in this case, a squared is going to be equal to negative b, which is going to be whatever 3 times 576, plus or minus square root of b squared times 4, or minus 4 times a, which is 1, c, which is 576 squared, all divided by 2a. I don't know what those values are, but you can try them on it. See if you can solve and get those numbers. All right. I'll give you another second. Again, I'm going to post these in case you missed something. All right. So classifying conics from the general equation. We talked about this in algebra 2. The standard or the general form of a conic looks like this, right? Ax squared plus bxy plus cx squared plus dx plus ey plus f equals 0. To translate from one form to the other, you might have to complete the square and do all that other stuff. But what I wanted you to recognize here is if right now we're not dealing with any xy term. B is equal to 0 from what we've been doing so far. We're going to look next time at when B is not equal to 0 and we have a B term. What's going to happen is that it's going to rotate the conic. So we're going to deal with that next time. But what you need to be able to recognize, if A, so let's ignore the BX term for BXY term for right now. If A is equal to C, it's going to be some kind of circle. If the product of A and C, or what that means is that that A is not equal to C, but the signs are the same. If the x squared term and the y squared term, the signs are the same and they're not equal, it's going to be an ellipse. Here, if one of the squared terms is 0, then it's going to be a parabola. If it's the x squared term plus some 0 y squared, then it's going to be a vertical parabola. if it's a y squared term, but no x squared term, it's gonna be a horizontal parabola. If the product is less than 0, which means one is positive and one is negative, we're gonna have a hyperbola like we looked at today. So you can tell just by the A and C terms what kind of conic you have. And like I said, when we get to next lesson, we're going to talk about what B means. And those are really fun, trust me. But for now, if I just look at the standard equation, I know exactly what it is just by looking at it. Here, my x squared and y squared term are both positive. They're not equal. Since they're both positive and not equal, it's an ellipse. Here, I've got a y squared term. I don't have an x squared term. So that's going to be a parabola. It's going to be a horizontal parabola. Here, I've got a positive y squared term and a negative x squared term. This tells me I am going to have a hyperbola, and it's going to be vertical. Here, my x squared and y squared terms are equal, so it's a circle. You'll notice I never even looked at these terms to determine what kind it is. Here again, my x squared and y squared terms are both 1, both positive 1. So that would be a circle as well. All right. I told you we would get done early, but you have plenty of stuff to work on. There's in-class worksheet. Again, you can turn that in today if you want to. If you don't get done with it, you can certainly take it home. The website should be open to the correct one. And your Alex quiz is still open. And the quiz on Wednesday, I believe it's like 7, 8, 9 questions somewhere in there. No calculated, okay? So there's not going to be any ones with big, huge calculations. It's going to be ones that you can take the square root of and not have to come up with big, long decimal numbers. So know your formulas, okay? That's what I need to emphasize. Know your formulas. If you don't know your formulas, you're going to have a bad time. All right. And that is where we're going to stop for today.